Welcome to our comprehensive guide on pulse analog communication. In this video, we'll explore the fundamental concepts that form the backbone of analog pulse transmission systems. From understanding the basics of how information is represented using pulses to delving into the key techniques that make reliable communication possible, we'll cover it all. Whether you're a student, an enthusiast, or a professional looking to refresh your knowledge, this journey will clarify essential ideas like sampling, aliasing, and various modulation methods. Let's begin by setting the stage for why pulse analog communication is so important in modern electronics and telecommunication. Pulse analog communication is a method where analog signals are represented by a series of pulses. These pulses carry information about the original signal, allowing it to be transmitted efficiently over various media. Unlike continuous analog signals, pulse analog signals are easier to process and less susceptible to noise. This makes them ideal for many applications, including telephony and data transmission. In this scene, we'll explore the basic structure of pulse analog signals and how they differ from both pure analog and digital signals. Understanding this distinction is crucial as we move forward. Sampling is the process of measuring the amplitude of an analog signal at regular intervals. These measurements, or samples, are then used to reconstruct the original signal. Sampling is a foundational concept in pulse analog communication because it allows continuous signals to be represented in a form suitable for pulse modulation. The accuracy of this representation depends on how frequently the signal is sampled. In the next scenes, we'll discuss the critical rules that govern sampling and why they matter for communication systems. Sampling theorem, also known as the Nyquist theorem, states that to accurately reconstruct an analog signal from its samples, the sampling rate must be at least twice the highest frequency present in the signal. This minimum rate is called the Nyquist rate. If the sampling rate is too low, important information can be lost, leading to distortion. The sampling theorem is a cornerstone of modern communication systems, ensuring that signals can be faithfully transmitted and reconstructed. Let's see why this rule is so critical in practice. Using the correct sampling rate is essential for accurate signal representation. If the rate is too low, the sampled signal may not contain enough information to reconstruct the original waveform. This can result in errors and loss of detail. On the other hand, sampling at a much higher rate than necessary increases data size and processing requirements without significant benefits. Engineers must balance these factors to optimize system performance. In the next scene, we'll explore what happens when the sampling rate is insufficient. Aliasing occurs when a signal is sampled at a rate lower than the Nyquist rate. In this case, different frequency components of the signal become indistinguishable from each other, creating distortion in the reconstructed signal. This phenomenon can severely degrade the quality of communication, making it impossible to recover the original information accurately. Understanding aliasing is crucial for designing effective communication systems. Next, we'll discuss how to prevent aliasing and ensure signal integrity. To prevent aliasing, engineers use anti-aliasing filters. These filters remove frequency components above the Nyquist frequency before sampling occurs. By limiting the signal's bandwidth, anti-aliasing filters ensure that only frequencies that can be accurately sampled are present. This step is vital in both analog and digital communication systems. Proper filtering preserves the integrity of the transmitted information and prevents unwanted artifacts in the reconstructed signal. Aliasing filters are typically low-pass filters that allow only frequencies below a certain cutoff to pass through. By blocking higher frequencies, these filters protect the sampled signal from aliasing effects. The design of an anti-aliasing filter depends on the application and the characteristics of the signal being processed. In audio systems, for example, the filter must be carefully tuned to preserve sound quality while eliminating unwanted frequencies. Let's look at how these filters are implemented in practice. Pulse amplitude modulation, or PAM, is a technique where the amplitude of each pulse represents the instantaneous value of the analog signal at the sampling moment. PAM is one of the simplest forms of pulse modulation and serves as the basis for more advanced techniques. It is widely used in communication systems due to its straightforward implementation. In the following scenes, we'll explore how PAM works and its advantages and limitations. Pulse amplitude modulation. The analog signal is sampled at regular intervals, and each sample is used to set the amplitude of a corresponding pulse. The resulting sequence of pulses forms a signal that can be transmitted over a communication channel. At the receiver, the original analog signal can be reconstructed from the pulse amplitudes. PAM is simple to implement but can be sensitive to noise, as any disturbance affects the amplitude directly. Pulse amplitude modulation is used in various applications, including early telephone systems and some types of digital communication. Its simplicity makes it attractive for systems where bandwidth is not a major concern. However, because PAM is susceptible to noise and interference, it is often replaced by more robust modulation techniques in modern systems. Understanding PAM is still important, as it forms the foundation for more advanced methods. While PAM is easy to implement, it has significant limitations. The main drawback is its sensitivity to noise, which can distort the amplitude of the pulses and lead to errors in the reconstructed signal. Additionally, PAM signals require a relatively large bandwidth compared to other modulation methods. These limitations have led to the development of alternative techniques that offer better performance in noisy environments. Pulse width modulation, or PWM, is another important pulse modulation technique. In PWM, the width of each pulse is varied in proportion to the amplitude of the analog signal at the sampling instant. Unlike PAM, the amplitude of the pulses remains constant, making PWM more resistant to certain types of noise. PWM is widely used in applications such as motor control, audio synthesis, and power regulation. Pulse width modulation. The analog signal is sampled, and the duration or width of each pulse is adjusted according to the sampled value. The amplitude and position of the pulses remain constant while only the width changes. This approach makes PWM signals less susceptible to amplitude noise, as information is encoded in the time domain. PWM is especially useful in systems where power efficiency and noise immunity are important. PWM is commonly used in controlling the speed of motors, dimming lights, and generating audio signals. Its ability to efficiently control power delivery makes it ideal for embedded systems and power electronics. In audio applications, PWM can be used to create high-fidelity sound with minimal distortion. The versatility and robustness of PWM have made it a standard technique in many modern electronic devices. Pulse width modulation offers several advantages over other modulation techniques. It is highly efficient, as power is only delivered during the pulse duration. PWM signals are also less affected by amplitude noise, making them more reliable in noisy environments. Additionally, PWM can be easily generated and processed using digital circuits, which is a major benefit in modern electronics. Despite its many advantages, PWM is not without limitations. The main challenge is the generation of high-frequency harmonics, which can cause electromagnetic interference (EMI) in sensitive circuits. Careful filtering and circuit design are required to minimize these effects. Additionally, PWM may not be suitable for all types of signals, especially those requiring precise amplitude representation. Pulse position modulation, or PPM, is a technique where the position of each pulse relative to a reference is varied according to the amplitude of the analog signal at the sampling instant. The amplitude and width of the pulses remain constant while only their timing changes. PPM is valued for its resistance to amplitude and width noise, making it suitable for certain communication environments. Pulse position modulation: the analog signal is sampled, and the timing of each pulse is adjusted based on the sampled value. The amplitude and width of the pulses do not change, which makes PPM signals less susceptible to certain types of noise. However, precise timing is required for both transmission and reception, which can complicate system design. PPM is often used in optical and wireless communication systems. Pulse position modulation is widely used in applications where noise immunity is critical, such as in optical fiber communication and remote control systems. Its resistance to amplitude and width noise makes it ideal for environments with high interference. PPM is also used in some wireless communication protocols, where timing accuracy can be maintained. Understanding PPM helps in designing robust and reliable communication systems. PPM offers several advantages, including strong resistance to amplitude and width noise. This makes it particularly useful in environments where signal integrity is a concern. PPM also allows for efficient use of bandwidth, as pulses can be closely spaced without overlapping. However, the need for precise timing can make implementation more complex compared to other modulation methods. Main limitation of pulse position modulation is the requirement for precise timing synchronization between the transmitter and receiver. Any timing errors can lead to incorrect interpretation of the signal. Additionally, PPM systems can be more complex to design and implement, especially in environments with variable delays or jitter. Despite these challenges, PPM remains a valuable tool in many specialized applications. Now that we explored the main pulse modulation techniques, let's compare their key features. PAM is simple but sensitive to noise. PWM offers better noise immunity and efficiency, while PPM excels in environments with high interference but requires precise timing. Each method has its own strengths and weaknesses, making them suitable for different applications. Understanding these differences is essential for selecting the right technique for a given communication system. Selecting the appropriate pulse modulation method depends on several factors, including the nature of the signal, the communication environment, and system requirements. For example, PAM may be suitable for simple, low-noise systems, while PWM or PPM might be better choices in noisy or power-sensitive environments. Engineers must weigh the trade-off between complexity, noise immunity, and bandwidth efficiency to make the best decision. Bandwidth is a critical consideration in pulse analog communication. Each modulation technique has different bandwidth requirements, which can impact the overall performance of the system. PAM typically requires more bandwidth than PWM or PPM, which can be a limiting factor in some applications. Efficient use of bandwidth is essential for maximizing data transmission rates and minimizing interference. Noise and interference are ever-present challenges in communication systems. Pulse analog techniques must be designed to minimize the impact of these disturbances. While PAM is particularly sensitive to amplitude noise, PWM and PPM offer better resistance. Understanding the sources and effects of noise helps engineers design more robust systems that maintain signal integrity under real-world conditions. After transmission, the original analog signal must be reconstructed from the received pulses. This process involves filtering and, in some cases, interpolation. The accuracy of reconstruction depends on the quality of sampling and the effectiveness of anti-aliasing filters. Proper reconstruction ensures that the transmitted information is faithfully recovered, which is the ultimate goal of any communication system. Filters play a crucial role not only in preventing aliasing, but also in reconstructing the original analog signal from the sampled pulses. Low-pass filters are commonly used to smooth out the pulse train and recover the continuous waveform. The design and quality of these filters directly affect the fidelity of the reconstructed signal. Proper filtering is essential for high-quality communication. While this video focuses on analog pulse communication, it's important to note the differences between analog and digital pulse systems. Digital pulse communication uses discrete values, offering greater noise immunity and easier error correction. Analog pulse systems, on the other hand, provide a more direct representation of the original signal, but are more susceptible to noise. Both approaches have their place in modern communication technology. Evolution from analog to digital communication has been driven by the need for higher reliability, efficiency, and scalability. Digital systems can easily implement error correction and encryption, making them ideal for modern networks. However, understanding analog pulse techniques remains important, as many legacy systems and specialized applications still rely on these methods. Pulse analog communication has a rich history, dating back to early telegraph and telephone systems. These techniques laid the groundwork for modern communication technologies, influencing the development of digital systems. By studying the evolution of pulse modulation, we gain valuable insights into the challenges and solutions that have shaped today's networks. Despite the dominance of digital systems, pulse analog communication is still used in various applications. These include specialized industrial controls, legacy telecommunication systems, and certain types of audio and video transmission. The principles of pulse modulation continue to inform the design of new technologies, ensuring their relevance in the ever-evolving field of communication. Let's recap the key points covered in this video. We explored the basics of pulse analog communication, the importance of sampling and the sampling theorem, the challenges of aliasing, and the role of anti-aliasing filters. We also examined the main pulse modulation techniques, PAM, PWM, and PPM, comparing their advantages and limitations. These concepts are fundamental for anyone working in communication technology. Deepen your understanding of pulse analog communication. Consider exploring textbooks, online courses, and technical articles on the subject. Many universities offer detailed lectures and lab exercises that cover both theory and practical implementation. Staying updated with the latest research will help you apply these concepts effectively in real-world scenarios. In working with pulse analog communication, common mistakes include choosing an incorrect sampling rate, neglecting anti-aliasing filters, and underestimating the impact of noise. Avoiding these pitfalls is essential for building reliable systems. Always verify your design choices with simulations and practical tests to ensure optimal performance. As technology advances, new pulse modulation techniques and applications are emerging. Innovations in signal processing, materials, and circuit design are pushing the boundaries of what's possible. Researchers are exploring hybrid systems that combine analog and digital methods for improved performance. Staying informed about these trends will help you stay ahead in the field. For engineers working with pulse analog communication, practical tips include carefully selecting components, simulating designs before implementation, and thoroughly testing systems under real-world conditions. Pay attention to details like filter quality, timing accuracy, and noise sources. These best practices will help you build robust and efficient communication systems. Let's look at a case study involving audio transmission using pulse analog communication. In this scenario, the audio signal is sampled, modulated using PAM or PWM, and transmitted over a channel. At the receiver, the signal is demodulated and reconstructed. This process highlights the importance of proper sampling, filtering, and noise management in achieving high-quality audio. Industrial control systems, pulse analog communication is often used to transmit sensor data and control signals. Techniques like PWM are favored for their noise immunity and efficiency. Proper implementation ensures reliable operation in harsh environments, where electrical noise and interference are common. This case study demonstrates the practical value of pulse modulation in real-world application. Remote control systems, such as those used in drones or model vehicles, often rely on PPM for signal transmission. The technique's resistance to amplitude noise and efficient bandwidth use make it ideal for wireless communication. Accurate timing and synchronization are critical for reliable operation, highlighting the importance of precise system design. Summarize: pulse analog communication encompasses a range of techniques for representing and transmitting analog signals using pulses. Key concepts include sampling, the sampling theorem, aliasing and aliasing filters, and the main modulation methods, PAM, PWM, and PPM. Each technique has unique strengths and is suited to specific applications. Mastery of these concepts is essential for anyone involved in communication technology. As we look to the future, pulse analog communication will continue to evolve, driven by advances in technology and new application demands. Whether in legacy systems or cutting-edge research, the principles discussed in this video will remain relevant. Staying curious and informed is the key to success in this dynamic field. Before we conclude, let's review a glossary of key terms: sampling, Nyquist rate, aliasing, anti-aliasing filter, pulse amplitude modulation PAM, pulse width modulation PWM, and pulse position modulation PPM. Understanding these terms will help you navigate the world of pulse analog communication with confidence. Thank you for joining us on this exploration of pulse analog communication. We hope this video has clarified the essential concepts and inspired you to learn more. Whether you're designing systems, studying for exams, or simply curious about how communication works, these principles will serve you well. Keep exploring and stay connected to the world of technology. This concludes our video on pulse analog communication. We appreciate your attention and hope you found the content valuable. For more in-depth tutorials and resources, continue exploring the fascinating world of communication technology. Until next time, keep learning and innovating.